let's just replay this real quick. So this is the title of the talk. This is the team, my associates and I. We've been taking a break from 2023 to till 2024-ish something, end of 2023 to end of 2024, working on a car. Why did we start that project? Because we were growing concerned about the safety and the opacity in the automotive world and transport world. The fact that it's a little bit opaque, the what is put in place to protect your cars from a software perspective. The fact that also there's no Linux for cars in the sense that you can replace the software that is running in your car with something open source. And that several parts from different manufacturers that do exactly the same function should be, it should be possible to use them in different brands and different cars. So upgrading a vehicle can mean different things. It can be an engine swap, EV retrofit, so replacing the thermal engine with an electrical one. It could be adding features that the car didn't have or didn't even have from the manufacturer, but that you can build yourself, like an infotainment system. Adding some assisted driving or autonomous driving features or remote control. What I'm showing in this presentation is not road certified, and it will never be. And that's the donor car. It's a 2007 Polo Blue Motion series. It was a diesel engine, 3-cylinder. It was making a lot of noise, so really not that great, but it was very fuel efficient. Some of the upgrades that we've done to the car itself, the mechanical work is not going to be completely shown here, but I'm going to explain the software part and the hardware components that we built. I let the people in the video to just look at that slide because I've covered it already. But we did that thanks to open source projects, mainly and especially Elixir and Nerves, which are the core technologies we used in the Raspberry Pi specifically. Elixir is a language that runs on the Beam, which is the Erlang virtual machine. And Nerves is a firmware builder, firmware development tool that is built in Elixir, and that also uses Buildroot, which is a Linux build system, which just gives you the right amount of Linux that you need to run your software. The rest of the technologies we've used is Vue.js for everything that's web front-end, Flutter for the infotainment screen, and then the APIs that we've built are in Phoenix, which is an Elixir web framework. Elixir provides pattern matching and really cool other functional language features, and that makes our development life much easier than if we would have done all of this in Python or C. And Nerves, I think I've covered it already. Understanding the car language, most cars, pretty much all cars, still have a CAN bus, which is 2 wires, 2 twisted wires that are running across your car, on which several components are connected, and they're emitting messages at a specific frequency. And that's what we see here on this screen. Every message, every component on the bus will emit messages that have a specific ID and then a series of bytes representing the data that they're sharing. And it really looks like, like this, values changing from time to time. And you have to figure out which is what, which is which. I talked about the fact that there's a community of people sharing some of those traces and files. It turns out that the OpenDBC project is one of those. Those are people that come out of AI is a company in the US that is actually providing assisted driving features to existing cars. And they do that by reverse engineering some CAN messages from the cars. And so they have a whole community of people sharing this information there. So I had a question before we started re-recording, which was how much did we have to reverse engineer, or how did we reverse engineer? For simple things in the car, like the handbrake, we would just look at the screen that you see there with all the blinking values. Then we would just pull the handbrake and see which value changed, and then pull it down and see if we found the correct message. And then we would deduct the value based on what we did. For other parts, for instance, like the ignition lock, it's actually interesting because when you insert the key, there's a value that changes. When you turn the key, there's another value that changes. And then when you actually, do the ignition part, that's even another value that gets changed. And so this is the kind of stuff that you have to figure out by yourself if you really want to make that seamless integration. And once you have these messages decoded, then you can start creating that translation platform. So let's look at the components themselves. So what we have today, at least in the car that we've built, is 5 different CAN networks because we have different types of components. I'm going to start with the green ones. All the green boxes are the original Polo, Volkswagen Polo components. So there you have the ABS, so the anti-lock braking system, the dashboard, which is the instrument cluster, ignition lock, doors, and all other components that exist already in the car. There's also another component that is on the complete left on a separate CAN, which is the steering pump. And I'll come back to this one in a minute because it's an important one. Then you have at the top the Nissan components, the inverter, the motor, and the charger. We built the battery ourselves, which means that we didn't really buy an existing Nissan Leaf battery management system. So we actually bought an Orion BMS, which allows us to balance the cells and make sure that we're not over capacity or anything. That is an Orion BMS, which is on its own CAN network. And then we also have what we call the MISC CAN, which also has components that don't necessarily belong anywhere else. The steering pump of the Polo and the brake booster. I'll explain. Yeah, is there a question? No, just a microphone on. So we started, with one simple objective in mind. The first step was we need to get the Leaf motor to spin. And so we opened it up and started to figure out where to measure things, where to connect in order to figure out where the CAN was and all that. And we needed to find the right CAN messages to power up the motor. Fortunately, the Nissan Leaf is one of the most sold EV in the world. And it's easy to find spare parts, and it's also easy to find people that have already tried to hack it. And so by combining different files, different CAN traces, so those DBC files, which contain CAN messages specifications, by combining this with some information we found online, we could figure out what messages to send to the motor to make it spin, and also what messages we needed to send the motor for it to wake up. Because in modern cars, sometimes there is a handshake happening over the CAN, or there is a message that needs to be sent at a specific frequency in order for the components to wake up, because it basically tells them, hey, there is actually a gateway somewhere that is saying to everybody, now you can wake up. And we need to simulate these messages. We need to basically fake it so that they believe they're in a real car and they believe that they can actually function properly. And at some point, we had figured out the messages to send to the motor, but we wanted to really have the end-to-end, right? We wanted to have a gas pedal and the motor. So the first thing that we started building was that specific process. And it started by taking the gas pedal from the Polo, hooking it up to an Arduino, and then trying to make it work and emit CAN messages instead. So a gas pedal is basically 2 potentiometers, and they're both calibrated differently so that you can actually, there's a formula that you can use to make sure that the readings are always in a specific range, so that if you see a difference, it means the pedal is malfunctioning and that you should probably not treat the output the same way as if it was safe. So it's a safety feature in gas pedals. You have two potentiometers and you have to read them both. For the sake of this project, we only read one, so it's not really great. It's not super safe, but it's good enough for what we're doing. And what we did was simply connect that gas pedal to an Arduino. And then from that Arduino, we emit CAN messages on the small SPI CAN module that you see on the breadboard. You also see that we have a PRND on the breadboard because at first this Arduino controller, was both getting the throttle position and also the automatic gear that we wanted. And that's what we started using to control the motor afterwards. Then we had the contactors. Contactors are basically a relays that you need to activate in a specific order to make sure that you have pre-charge ramping up in the motor instead of having all of the voltage and current at the same time, which could fry the electronics in the motor. And so you have to do things in a specific order with a big resistor so that it really ramps up over a very short period of time, by the way, but it has to ramp up. It cannot be instantaneous. Otherwise, you fry a lot of components in the motor. And we also controlled those contactors, so those relays, with Arduinos connected to CAN. And so all of this was CAN based. And it means that the Raspberry Pi that we used in the beginning was sending CAN messages in the right order. So we basically recreated what you would find in a car, which is a CAN gateway that will make all of this work together. The big difference is that we created this with off-the-shelf components like a Raspberry Pi and with very high-level software, which is Elixir, which is not something you would see every day. And now you see the whole setup from the beginning. You see the very first component, which is the vehicle management system, which is the new brains of the car. You see the gas pedal with the car controls controller, so what allowed us to select the gear, and also the gas pedal, getting the gas pedal value and setting it over CAN, and then the contactors controllers. And that's really the first time, so you can probably not hear the sound, but that's the first time we actually made the motor spin with the gas pedal. So at that point, we had a somewhat working solution. Now the next step was just making the wheels spin. And that meant that we had to put that motor into the car. Obviously, the motor was not made for a Volkswagen Polo, so we had to create a new motor support that was welded on the chassis. And we decided to keep the original gearbox because not keeping it would have put this project in a completely new space. So we decided to keep the gearbox. But the blueprints of the leaf motor and the gearbox didn't match, obviously. So we had to CNC some aluminum plates that we had to weld together that were matching perfectly the blueprints of those two pieces. And we had a junction piece that we needed to connect the gearbox axle to the motor. So all of that was also made in-house. It turns out we have a small handmade. It's something a DIY. We have a DIY CNC machine that we used to CNC the aluminum plates. And Loic, my associate, also had what we needed to fabricate the rest of the pieces. A lot of 3D printing involved as well. You'll see that in a minute, but those are the two courageous Prusa 3D printers that we used to print everything we needed for this project. There's about 200 pieces that had to be printed, some of them several times. There's weeks of printing time in this project as well, and a lot of failed designs. But that would be way too long to explain. Now, you've seen the Planck prototype where we were when we were basically trying things out. And this is what it looks like now in the car. So everything was 3D printed besides the actual plugs, obviously, that we bought already made. But we had to wire all of these ourselves. So we created all of the cabling ourselves. And we created some custom SPI heads so that we could really make sure that everything was really tight and that we would not have something disconnect when we were driving. But all of the boxes were 3D printed. Everything was 3D printed besides the obviously the Wago plugs and the actual plugs themselves. So what you have on the left is the vehicle management system. That's really, again, the brains of the car. It has 5 CAN chip. So those are MCP 2517, all running on SPI, on the SPI bus. So a serial peripheral interface. We also have the controllers. Those are Arduinos. Those are the ones that will, like I showed, get the information from the gas pedal, control the contactor, so the relays for the motor. And we also have a controller that actually is used to control the steering column, but I'll come to that in a minute. And then we have some hubs that are providing 12-volt power and CAN connectivity. And we do have some of those hubs, several of those hubs in the car with some empty ports. So we can still come and plug additional components that we would want to add one day. So we still have stuff to extend the car. The VMS, so the vehicle management system, also has a web interface. So at any time you can basically connect and see real-time values that are happening on the car. But this is a screencast that I've done when we were recording a video for a presentation. I'll share the link afterwards so you can see the car actually being driven. And you see the RPMs, the voltage on the engine, on the motor. You see the speed of the car, the torque, the throttle. We can also see all of the network status. We can also recalibrate the car controls. So there's a lot of different things that happen in this interface and that we added over time. But it gives us valuable information about what the car is, well, how the car is behaving in real time. All right. Just maybe one word about the controller on Arduino. When we started doing the work on the car, we used a traditional, Arduino development lifecycle in the sense that each time we wanted to change the firmware on the Arduino, we would plug it with a USB cable and then change the firmware. And then we decided that it was not really convenient. So instead, we created what we call a generic controller. What it does is that all of them have exactly the same code, but based on the configuration they will receive from the vehicle management system, they will behave differently. And so we have created an adoption process that you can start in the vehicle management system, which will, for instance, in the vehicle management system, will say, okay, now I need a front controller. Okay, fair enough. And I have a configuration from the front controller. By pressing a specific button on the controller, it will get into adoption mode and wait for a frame for the configuration. So over the CAN bus, it will receive a configuration frame, and then it will change its internal configuration to the specific use case it's designed to. And we can then basically decide whenever we want to change the configuration of a controller without unplugging it, plugging it to a USB cable, and blah, blah, blah. So now the same code runs on all controllers, and the configuration is defined at adoption process. And we never really changed the code since then. So it's been a year that we haven't touched these, which allows us to really have something super flexible for all the use cases that we want. And you have the OVCS functions there, the physical pin, the OVCS pin. So all of that is really the configuration that's baked into the code. And based on that, we know exactly what to expect from that controller. Then you have the infotainment system, which is giving us some information about what's going on in the car. That was one of the first versions that didn't really do much, but and it also is used to have the gear selector on it. So it's a touch screen. So it's basically where you will select if you want to go in reverse or if you want to go into drive or whatever. And again, nerves and flutter were used for this one. This is what it looks like with the components in the car. You also notice an RC car right there. It's actually a small scale of the full car. That's also something we've built. I won't really have time to go into this one, but a small scale version of the full scale car, because since we're working on self-driving capabilities, testing this on a full scale 1-ton car is a little bit dangerous. So we thought, why not try to run the exact same hardware and software stack on an RC car. It's a really interesting build as well, but it deserves its own talk. So what we've done is we welded some supports in the trunk of the car, put an aluminum plate, and then we basically screwed everything on this. So yeah, that gives you an idea of what it looks like in the car. Now, there's some adaptations we had to do. It turns out that if you have a thermal engine, at least for cars of that era, the brake assistance is provided by the depression that the thermal engine is creating. But if you remove the thermal engine, you don't have brake assistance anymore.
The mind of the other side. John. Mr. Vice President, thank you. I want to ask you about that 1.8.
All right. Yes, thank you. So since we didn't really have brake assistance anymore, we needed to find a way to get it. So we took what we call a brake booster, which is a component in Tesla cars. It's basically a hydraulic pump that will pump liquid into the braking system electronically instead of using the depression of the thermal engine. But we had to reverse engineer on this one. We had to reverse engineer some of the CAN messages to make it work. And we just installed it in the Polo and it worked. So for us, that was already done. Now, the steering pump, it's not a modern steering assistance in that car. It's still a steering pump that is operating really close to the wheels. And the problem with these kinds of steering pumps is that they only start when the engine is running. So typically what they will do is they will listen to messages on the CAN bus from the engine. And when they see that the engine is at the idle RPM level, it will start. So it's expecting, if I recall correctly, 800 RPM to start. Remember that we put it on a completely different CAN network because now that we have an electric motor in the car, when the car is idle, the RPM is 0, but you still want to be able to steer. So we need to, again, fake it. We need to make the pump believe that the engine is still there and that the engine is running at 800 RPM for it to start. And so that's why we had to isolate it in its own CAN network so that we could control this ourselves. We also built the battery, a lot of 3D printing involved there as well to, build all of the small plastic pieces you see there. So we got the cells and we had to build all the wiring was done by ourselves. It was a pretty tedious and stressful experience, to be honest, because we could probably die if we had made a mistake. But yeah, that's making it easier by doing your battery yourself. I don't recommend it, but it worked for us anyway. Now we didn't want to stop there, right? Because we knew we already could accelerate because we knew what kind of CAN messages we needed to send the motor to make it spin. Braking, maybe, we'll see. Steering, didn't really know what to do. The Tesla brake booster is something you can control via CAN message. Like I said, we had to reverse some of those CAN messages. And it turns out that from the first generation of the same component, we could figure out the messages we were missing for the second generation. And at some point, we had this working. So it's kind of funny because you really see the pedal moving when you send CAN messages. But there, what you see is basically the the pump is doing its job and braking by itself with CAN messages. So braking was done. And now steering. The original steering column of the Polo was not motorized at all. So we tried with a 2019 Polo steering column, which could fit in the car. But the problem we had is that we couldn't reverse engineer that one. This is the kind of things that I believe that today with LLMs, we could definitely make it work. There is probably a lot of knowledge that we were missing that just today, and I tried the other day trying to figure out again with that component, and it automatically gave me some leads on messages that I could send in order to wake the device up that we didn't even try back then when we spent weeks on this. So there is information that we have today that could probably save us some time today. So what we did, because it didn't work, we basically decided to remove the ECU from the steering column. So we just removed it and put our own servo motor on it. So we reused the steering column from 2019, but we basically used a servo motor that we could control ourselves, and we also added an angle sensor to it, so that we could know exactly at which angle we were steering. And that's what it gave at some point. So there you can see that we are remote controlling. So we're actually moving the wheels and also turning the steering wheel with the remote control, all through the platform that we built, so all through CAN messages. And that was really the moment where we had the car in a drivable state, but we still needed to finish the cabling and all that to make it really safe to drive. Well, what now? Like I said, we're working on different things. One of the things we're doing is adding a 4G gateway to the car, and also now looking into self-driving it, or at least assisted driving, and also interfacing with ROS2, which is a robotics platform. So we're experimenting with different types of bridges that we could build. And we're going to keep working on this. And in order to make this happen, we're also working on the small scale version of the car, which allows us to test all of that in a safe space instead of always moving the 1-ton car, which is quite big and dangerous. So that's it for me. I'm going to post the link to a video in the chat, so I can show you a little bit what the car is how the car is driving today. But I guess now is time for questions if you have any.
Yeah, thanks for that. So I had to leave the room there. I just realized that I had sent the wrong link to one of the Eventbrite, so half the people couldn't get in.
That's all right. Don't worry.
Rushing off. It's been a nightmare, mate. Really screw up this meeting. First, forgetting to press record, and then screw up with the invites. I think I'd be new to this, but I've been doing this for a long time now. Oh well. Live and learn.
There is a link for those who want to go see the video, and I will share the slides anyway at some point. But yeah.
Got a question in the room here?
I have a question, by the way. Thank you. My question is, what experience did the three of you bring to this if you triage it between software experience and car stuff? You've made some interesting software choices. You seem to be quite practical with cars. Is that your background coming to this?
All right. So if I understand the question correctly, it's what background did we each bring to the project? Okay. Okay. So all of the welding and metal work, that was Loic, basically. He's the one that has been playing with cars for a while, and he had experience in welding. He also brought, and we contributed for different things, but he brought also 3D printing skills. We have 3D printers at home, but he is the one that mainly also created all the pieces. For all the software platform experimented. So when you saw the gas pedal, the first prototype of the gas pedal, I was the one working on that component, for instance. So Thibaut and I worked a lot on more like the smaller hardware and software part. And Loic obviously also created the software with us at some point, but there was indeed a different skill sets being brought at different times. There's also a lot of things that a lot of paths that we explored and that we didn't really pursue. Like at some point I was playing with really working on the automated part with object recognition and all that. So, but this, we just stopped it at some point because we needed to focus on getting something, working and done at some point. But yeah, we all contributed everything that we could do. And we also learned a lot of things that we didn't know before by working on this project.
Thank you.
So Akil has a question. Akil?
Yeah, thank you for the great talk. I very much enjoyed it. I have two questions. It seems that you put a lot of effort and resource into this project. So I was wondering how much time did you take from the beginning until you reach this state in the project? Is the first question. The second question, I noticed that you are using the joystick or something like a joystick, so to accelerate the motor and to steer the vehicle. My question is there some translation or dumping the, in digital you go from 0 to 1. Is there some translation between them, and are you using some BID controller between the
Yes.
joystick and the, okay. So this is my second question. Thank you.
All right. So the first question is the time invested. So we left the company we were working for end of December 2023, and we started already just dismantling the car. There's a funny anecdote, by the way, because we started stripping the car out of so we removed the engine, we removed a lot of stuff from the car at the end of 2023 because we said, okay, let's get the car ready for us to work on the project. And then we started trying to reverse engineer the CAN messages, and we realized that maybe we should have left the engine in the car because there's a lot of stuff that was just not working anymore without a key part of the car. So we actually made our job harder by doing that. But anyway, so we started working on it end of 2023, maybe 1 day a week or something. And then for all of 2024, we were working 3 to 4 days a week. Not long days, to be honest. We would be starting at 10 a.m., finishing at 4 p.m., something like that. That would be for the whole of 2024. And then in 2025, we've still worked on it for 3 months, I would say, at the same pace. So all in all, that's not that much when you realize all of the things we had to do, like all the software and also the battery and all that. So everything, all of these things that we had to learn along the way, that was a lot of time invested. And also we put about 25K in parts and everything we had to buy to actually do this project. So there's a lot of investment as well. But I mean, when you think about this, 3 people doing that with the 25K invested, it's much less than an MBA that people would pay, tens of thousands. So we just decided to put our money somewhere else. Some people would buy expensive trainings. We would actually, do something to learn something. So it's just a different approach. But in the end, it was, an investment. We kept enough money in the company after we left in order to do that. And I think that's. I don't think we could have learned what we did in this project by paying a training or whatever. So it was worth it. And the second question was the PID controller. Yes, we do have a PID controller. Turns out there's a bug in it, by the way, but we fixed it now. But yes, we have a PID controller for the throttle and the steering angle. Hitesh, you have a question?
Yeah. Can you hear me? Yeah.
Yes.
Yeah, great. Nice project, by the way. I liked all the components
Thanks.
that you did. Yeah. I was going to say I did something similar.
Okay.
A lot of things resonated. Where I took a Ford KA car and put it in a driving simulator. So I mean,
Okay.
I didn't
Yeah.
I didn't convert it into EV, but the journey I went through was kind of similar. When you showed
Yeah.
the throttle, and I had some I have some pictures of that throttle as well. What I used in that also the driving because when you are driving car, the steering wheel self-centers sometimes, like because the road forces on the
Yeah.
wheel pushes the steering wheel to center. But when you are standing still, when the car is standing still, it doesn't self-center. So I had to
Yeah.
reverse engineer the motor as well. So I
Yeah.
basically cut the drive off. I mean the motor drive, and I had to install my own motor drive and control it.
Yeah. Yeah.
I did a
I see.
position control on that.
Yeah.
Similarly, but what I used Raspberry Pi for in that project was for the dashboard.
Yeah.
I made my own dashboard to do the graphics on the Raspberry Pi.
Yeah. I see.
But I use other things as well. So yeah, nice. Yeah, it's nice to see something similar around similar time frame as well. Actually.
Okay.
Around
Good.
23, 24. Something.
Well, if you have anything publicly available on GitHub or anything, you can share the link. I'd be interested to look into it.
It was in university.
Okay.
So they used it for participants to drive.
All right.
And also change the mode, like driving mode to auto mode as well.
Okay.
Self-driving. And then so a lot of studies were there done using that car. But I don't have any public link. I do have some photos and videos I could share, like on presentation, another time if that's suitable. But yeah, it was nice to see something similar.
Thanks. Yeah, sure. Thanks.
Is there kind of like a mailing list or WhatsApp group or something similar for this?
There's none. We just have the meetup. Oh, for you mean for what we did or for this meetup?
For this meetup, yeah.
Okay, I'll let Richard answer this one.
Sorry, explain the question.
I'm wondering if there is a kind of a mailing list or meetup.
Yeah.
WhatsApp group or something, or is it just meetup through meetup?
Yeah, we're on Facebook, unfortunately. Facebook's not the greatest platform, but yeah, if you go to Facebook and join just Raspberry Pi. But then you can also register by Meetup, and you can just every time you if you join just the Meetup group, then you'll get like all the information. All of our videos go onto YouTube, so there's lots of videos from the last few years. So yeah, there's lots of interesting projects out there.
Mm-hmm. Nice. Yeah. Thank you.
Yeah. Bruce, you have a question?
You're muted, I think.
Your microphone's not working.
Showing me.
Yeah, we can't hear you, Bruce. Bruce put a question into the chat. If you read the chat there, he's saying that his son owns a magazine called Performance VW. And it's interesting. I wonder if you'd be interested in doing an article for them.
Yeah, sure. Yeah, I answered in the chat that yeah, I still consider it a VW, not another car, but yeah, sure. I mean, it still has the body of a Polo, so. But yeah, sure, of course, yeah, it would be great. You can reach me. I'll drop my email for anybody who wants to reach out to me. Yeah, I think I didn't make any mistake. And then I see other questions.
Yeah.
You're looking at putting any mitigation to prevent CAN bus flooding. That's a good topic, actually. not yet. I mean, not in the platform, but that's definitely the kind of, you know, safety or security features that would be fun playing with. Because most of the modern cars, they actually have a CAN bus that stays on all the time. That's how. That's basically how most cars allow you to know where they're parked, or you know that you can start them from a distance or whatever. So there's always something that stays on, and usually there's a CAN bus that stays on. And so indeed, if you can physically access to that CAN bus, because sometimes it goes under the car or in the doors or whatever, if you can physically get there and just, you know, plug plug a CAN bus terminal on it, you can flood it, or you can get some messages out. So indeed, yeah, the physical access to CAN bus is still today an issue. I'm not in the automotive world, so I don't know how much it is still an issue. But indeed, that's something we realized as well, that there's stuff that's much more accessible that we think when you start, you know, stripping down a car and all that. There's a lot that you can access, you know, on EVs today, since the battery is at the, you know, on the floor of the EV. It might be a bit harder, but I don't know. It depends how they are made and how they have been engineered. I don't know. But yes, we haven't tried specific safety features yet. It's something we might try one day.
Sorry,
Right.
I don't know if you covered it when I was out of the room, but I was just wondering about the, I think you mentioned at one point that it's easy to update the firmware and things on the different devices.
Yeah.
Did you talk about that, or how does that actually work?
I did very briefly when I talked about the framework we use, so Nerves. It's actually something that let me maybe share the homepage of Nerves. So what it is a very small framework that gives you. So this is trying it out. So there's a lot of information on the website that I'm going to. So I'm going to do Nerves Elixir. All right. So what it does is that it gives you a kind of a development environment, so you can write your firmware, so which is just going to be your business logic in a way, as an Elixir app, and then you can just type in mix firmware. It will package it, and then you can burn it on an SD card and put in a Raspberry Pi, and then it starts. It's magic. Then you can connect to it with SSH, and then you have a terminal that is directly accessible for you to play with, or your software is basically running. So this is what we call the interactive shell in Nerves. It lets you type in some Elixir commands in there, so that you can get information about is your application running, or anything else that you might be needing there. And it also provides A/B partitioning out of the box. So it means that if you change your firmware on your local machine, you change it, you again do mix firmware, so you repackage the firmware. You do what we call a mix upload. So you basically say, now upload my firmware to the Raspberry Pi. On the Raspberry Pi, if the valid partition, you see here the firmware valid is B, for instance. If you now upload a new firmware to that Raspberry Pi with mix upload, it will put the firmware on partition A, and then it will restart the device. If the device fails to boot, it will automatically revert to the previously known partition, which is partition B. All of that comes out of the box without you having to do anything. This is just one of the small things that it provides you. It provides you much more than this, but that's just to give you an example that you can have, you know, something that's really easy to work with. If you have your devices connected to your network, you can just, you know, the development cycle is very fast, and that really helped us get started on this. Doing this with Python or whatever, with Raspbian, or even hacking your own distribution for this is not that easy. And you quickly reach the limit. When you really want to do something that requires a lot of updates on the firmware, you need to have something that is batteries included, like nerves. There are other options out there, obviously, but this is for anybody who likes doing functional programming and pattern matching in languages. Elixir is definitely the best for this, and really, really nice to work with. What's really cool as well is that the nerves ecosystem has we have something called Livebook, which is very similar to the Jupyter notebooks that you can find in Python. And what Livebook does is that it provides really, I'm just going to pass some links here in the chat, but it provides you with the notebook style experimentation directly on the device. So it means that you can really play around with Elixir and the functionalities of your Raspberry Pi straight from there. I've also written a few guides on how to interface with hardware with nerves. So I'm also contributing documentation to nerves from time to time. So there's a lot of cool stuff about this framework that I think if you're not into cars, or if you're not willing to get into a car project right now, the takeaway of this talk should be that you probably should have a look at nerves, because it's a really cool platform.
That sounds very useful. Sounds like a game changer in a lot of ways. Anyway.
Well, I don't know if it's a game changer, but at least it's something that really makes development faster and easier for us. And it also means you're not really interacting with a very low-level language, but you still get the performance boost that you would not get from Python or whatever, because it's running on the beam. That's something that's been used for decades in telecom. I mean, this is what's running in cell towers or whatever. So this is not it's fault tolerant. I mean, if something crashes, gets restarted automatically. It doesn't break everything. So really, really nice for embedded use cases, and especially also use cases in cars. That's probably not the best technology out there, but that's definitely something for hobbyists like us that allows us to go fast.
Cool. Any other questions in the room? Okay, Mark, thanks a lot. That was really interesting. Sorry for all the mix up today.
No worries.
Just